everybody. This is the first lecture in a little course about chromatic homotopy theory and algebraic K-theory. And today we'll just be talking about chromatic homotopy theory. So it's a subfield of stable homotopy theory. And in stable homotopy theory, you study these objects called spectra. I'm going to make a slightly bold move here and not tell you what a spectrum is, but only kind of do it by analogy. So there's an analogy between spectra and objects in the derived category of abelian groups. So what kind of things are these? So this is the derived category of an abelian category, category of abelian groups. Traditionally, you'd maybe think of it as a triangulated category, but kind of that's usually not enough structure to do the things one wants to do. In particular, in a triangulated category, you can form cones, but it's not functorial, so that's annoying. And more complicated kind of gluing constructions, or homotopy colimits as they're called, are more difficult to manage in the triangulated setting. So people consider various enhancements of triangulated categories, and one of them is something called a stable infinity category, which has very simple and straightforward axiomatics. So these are, maybe I should manage my board work a bit better. Where's the eraser? Yes, okay. So these are both actually co-complete stable infinity categories. So co-complete means it has all colimits. And they're actually generated by a single compact object. And in this case, it's just the integers sitting in degree 0. And in this case, it's an object called the sphere spectrum. So more similarities. There's a tensor product. There's a symmetric monoidal structure. With unit, the same the same compact generator that we've specified for each of these categories. And this symmetric monoidal structure interacts with colimits in a nice way. If you fix a variable and consider it as a functor of the other variable, then it preserves colimits. Another similarity is that that's one, two. Another similarity is that they both have T structures. With heart equal the usual category of abelian groups. So on this side, T structure gives you the notion of homology functors, which goes from D of Z to abelian groups. And here, the homology functors are rather known as homotopy group functors, but they also just land in abelian groups. There's a big difference. So a big difference is that here, in this case, Z does lie in the heart of the T structure. So the generator does lie in the heart, but in this case, the sphere spectrum, the generator here does not lie in the heart. And in fact, if you look at the homotopy groups, so pi I of this object in the sense of this T structure here, these are the stable homotopy groups of spheres from algebraic topology. So these are the, you take the colimit over D of pointed homotopy classes of maps from the D plus I dimensional sphere to the D dimensional sphere.
So those three structures are Of course, there are also trivial T structures, but usually the T structures are good enough so that every object is kind of a limit of.
Yeah. They're complete in both directions. Yeah. So everything is a limit of its Postnikov tower, and everything is a co-limit of its, the dual thing. Yes.
So in Spectra, it will be the Algebraic spectra, which are the heart.
Correct. Yes. So in this, the heart is abelian groups, and the functor implementing that is the Eilenberg-MacLane spectrum construction. Yes. Okay. So that's some similarities. But how can we see the difference between these two contexts? Well, one we already kind of mentioned. In some sense, the difference amounts to the non-triviality of the higher stable homotopy groups of spheres. If the higher stable homotopy groups of spheres were trivial, there would be no difference between these two situations. But that's not a very good way of understanding the difference, because these are too complicated, and we're probably never going to truly understand all the higher stable homotopy groups of spheres.
Some kind of z-linearity, I'm not sure what it means, but even if the homotopy...
No, it would be z-linear if... No, and what I said is true. It would automatically be z-linear. This will maybe be a bit clearer when I say something else. So, actually, let me maybe make a remark right now. So, this is not some weird, exotic context. This is actually extremely natural, and arguably more natural than this one. So, this pair of this co-complete stable infinity category and this object here is free on one generator, is free as a co-complete stable infinity category equipped with an object. Or initial, universal. So if you have any co-complete stable infinity category with an object in it, then there's a functor from this one, which preserves co-limits, sending the sphere spectrum to that given object. And in particular, and in fact, and this d of z is just modules over this Eilenberg-MacLane spectrum. I'll just call it z in spectra. So z you could say is the Postnikov the zeroth Postnikov truncation of the sphere spectrum. So if these were equal, if a sphere spectrum was equal to its zeroth Postnikov truncation, then
So you view Z as a ring object in the center of this higher.
Yes, but that structure, I mean, it follows formally from, say, this formula. I mean, it's the tensor product also preserves the connective part, and so of the T structure, and so this formula would equip this with a ring structure, even if you didn't know it had one. I mean, it's this. All right. So maybe there's an analogy like the sphere spectrum is to the integers as the category of finite sets, and isomorphism between them is to the natural numbers. So it's some kind of enhancement. So if you look at finite sets up to isomorphism, you have not just cardinality, but you have knowledge of symmetries, which is kind of like a pi1 thing. And when you do the group completion process of adding inverses, then somehow that turns this into the whole sphere spectrum.
There was this theorem on algebraic topology named after 3 or 4 people like Quillin.
Yeah, Barrett, Pretty, Quillin. Yeah. So that makes that precise. Yeah, exactly. So, okay. Right. Okay. So let's go back to the topic of how to feel the difference. So one way to feel the difference is somehow it lies in these stable homotopy groups of spheres. Another way to feel the difference is in terms of this T structure. the hearts are the same, but the way you build a general object out of the objects in the hearts is different. So another thing you could do is you could look at the x's, or what this ambient stable category thinks the x between abelian groups are. So in other words, Homs from something in the heart to a shift of something in the heart. And these, in this case, is just usual calculation of x of abelian groups, and in particular, there are no x above degree 1. But in this case, you see things like the Steenrod algebra. Say when you take fp, x from fp to fp, in this category, you see the Steenrod algebra.
So it is mixed. You have the x and it is mixed with the other.
Yeah, you have x'd I, so to speak. You have x'd I for all I. I mean, you know, it's not, it's, and it's this big algebra. That's more, the Steenrod algebra you can write down. It's more understandable than this. And maybe that's a slightly better way to feel the difference between these two things. But I'm going to talk about a third way to feel the difference, which has to, so another way to feel the difference. And these are the concepts of VN self-maps, which were produced in full generality by Hopkins-Smith in their paper, so nilpotence 2. So first of all, there's something you can do on either side of this analogy here, which is you can pass to, you can fix a prime p, and then you can consider not spectra, but p-local spectra, and you can consider not, you know, you can look at derived category of p-local abelian groups. A p-local spectrum can be defined as one all of whose homotopy groups are p-local abelian groups, if you like. So let's first discuss this category from the perspective of self-maps. So how would you understand to analyze a general M in the derived category of p-local abelian groups? Well, you could. The most important thing to look at is the self-map multiplication by p, which you have on any object there. And when you have this self-map, then there's two different operations you can perform, which are in some sense complementary. One is you can invert it, which is just, say, taking a colimit over iterating multiplication by p. Another thing you can do is mod out by it. So you can do m mod p, which is the cone or the cofiber of this multiplication by p map. And more generally, you could mod out by an iterate of this map, so p to the n, and you get a tower in this way. And by this procedure, you can decompose M. So sort of by purely formal reasons, you actually get a pullback square like this. You can take the limit of this tower, and that's the p completion. And then they're glued along some common locus, which is where you take this and then invert p on the outside. And then this is actually a pullback square. And what have we gained by decomposing M in this way? Well, we've reduced to something simpler. So this guy here actually lives in D of Q. So Q is what you get when you invert P in Z1 over P. And Q is a field. So that's very simple linear algebra, even derived linear algebra. Everything is just completely straightforward when you're working over a field. So this guy is very easy to analyze. And over here, this, at least the first step, m mod p, also belongs to a field. So, and more generally, m mod p to the n belongs to kind of just a nilpotent thickening of a field. So not too hard to analyze.
It's not a fully faithful now.
You're correct.
It's not
So yes. Is not fully faithful. Yes, absolutely correct. So there's a warning that while it's true on the level of the hearts, that an FP module structure is just a structure on an abelian group. It's just a condition. It's the condition that P acts by 0. On the level of derived categories, that's not correct, as you can see by comparing X's.
I also encountered this thing, I don't know if it's relevant here, that you can start with something in the derived category, let's say of FP, then you can take the mod P, and then this is in this, so in this category, it says FP, derived FP category. Then you can view it in DZ and apply the enrichment of the enhancement that I said before, that is taking this mod P. Actually, it was not in this situation, but something related. It is not clear that the two ways to lift to this Z mod P are exactly the same. I mean, it was not.
Yeah.
In some case, it was not obvious.
Yeah, one has to organize things to understand such questions. Let me move on from this point. But just to say that we've achieved something by this simplification. We've reduced linear algebra over a one-dimensional domain to linear algebra over zero-dimensional things. Okay. So what happens when we try to do this in spectra as opposed to in abelian groups? So now we take a spectrum instead, a p-local spectrum. Well, we still have multiplication by p-map. But if you want to, one thing you can do is and functorial. One thing you can do is you can just produce multiplication by p-map on S and then tensor this with M. So if you want to, so you still have a multiplication by p-map, and you still have, for the same reason, you have the same pullback square. It's purely formal category theory, basically. And now the first piece of good news is that this still just lives in D of Q. And the reason for this is that Serre's theorem implies that, so if you take pi I of S tensor Q equals 0 for I bigger than 0. So once you've rationalized, there actually is no difference between stable homotopy theory and pure algebra. And the rational spectra are the same thing as the derived category of Q. So once you're p-local and you invert p, then you're rational. And so so this part, still you live over a field, you're happy. So the difference comes down here. So in contrast to the DZP, so M mod P, let me say doesn't live over a field. A nilpotent thickening of a field. And how can we test that? There's another self-map, non-trivial. That appears. So let me make just a formal definition so that we, so let's say for M in a spectrum, so a self-map of M of degree D in Z is a map from a d-fold shift of M to M. And let me say that two self-maps Fg, potentially of different degrees, are equivalent if there exist integers n and m, positive integers, such that f to the n is homotopic to g to the m. Yes, so that's iterating f. So if you have a self-map, you can compose it with itself. A self-map of degree d composed with itself gives you a self-map of degree 2d.
2D.
Yeah.
So in particular, the two Ds should have the same sign.
Yes.
They should have the same sign.
Yeah, d will actually always be positive. I mean, you know. Yeah, it doesn't have to be for the formalism, but in our case, it will be positive.
And of course, what you wrote is trivial because you could take 0 and then it is okay.
No, it depends on natural numbers, yeah.
Well, it depends on your definition of n, I guess. But when I wrote it, I did say positive integer. So, thank you. Yeah.
Before we go on, what
Yeah.
about right low corner, which you discussed?
Sorry?
What about right low corner, which you discussed?
Oh, but it also lives in dq. I mean, and once p is inverted anywhere, then you're living in dq. Yeah. Okay, so given a self-map, you can form, so a self-map F. You can form, you can invert F, and that's again just a colimit of M, and then you have to, well, maybe you go sigma minus dm, sigma minus 2dm. And you can also form M completed at F. And these only depend on the equivalence class. So all we're going to use these self-maps for is to either invert them or complete along them. So we only care about the equivalence class of the self-map.
But the automorphism group will act on the triangular somehow.
Sorry?
If the equivalence is not, there is a space of equivalences, more or less.
You're right. Yeah, you're right. So let me just say that the isomorphism class of these objects only depends on the equivalence class. It will also turn out that you have something better, that these will both promote to functors in the cases that we're going to be considering. But this is because they have an alternate expression. So perhaps I'll explain this later. So no, I'm not claiming anything in general, but in the situation that we'll consider, these will actually be functors. M goes to M1 over F, and M goes to M completed at F for the F that we're going to be considering. But we haven't gotten there yet, so let me just...
Those kind of things should be more rigid,
Yeah.
because kind of organization of competition
Yeah.
along something, so you cannot have extra automorphism.
Yeah, exactly. Yeah, it's some localization in both cases. It'll be some localization. Yeah. Okay, so So then the theorem, so Hopkins-Smith, so let me stick to the case of the sphere spectrum. It's not really relevant, but so there exists a canonical equivalence class of self-maps of any s mod p to the n, and it's always of degree some multiple, which is not well determined because of the equivalence class, some multiple of 2 times p minus 1. And these self-maps are called V1. And I'm not going to yet tell you the property that uniquely characterizes this equivalence class of self-maps, but I'll still tell you something about it. So I want to express somehow that it's a non-trivial operation. First, one thing is that if you take this s mod p to the n and then invert V1, then this is not 0. So you can't take V1 equals 0, or more generally, you can't take V1 to be nilpotent.
Yeah, and on Z mod P, it is 0.
On Z mod P, it is 0, correct, yes. So 2 is that if you take S mod P to the n V1, this is also non-zero. So you also can't take V1 to be identity map of degree 0. Or you can't take V1's not an isomorphism. Or maybe I should say, let's say complete along V1, yeah, and that's non-zero. It's the same thing.
What is the localization? This you didn't define.
This? Yes, I did.
No, completely defined, but that localized at you wrote before without completion, which was not well defined, which was not explained.
Excuse me?
S bracket P.
S bracket P. Oh, that S. Oh, yes. Well, that's just inverting everything prime to P. You mean?
But before you wrote, instead of V1 roof, you wrote something like localization.
Oh, no. Sorry, that was just modding out. You take this guy and then you mod out by V1. Take the.
Okay, no, you don't have the community algebra. Okay.
Yeah.
Mod V1.
Okay, and then it continues, and I continue. So then you're free to play this same game with breaking S mod P to the n up in terms of this completion and this localization, this inverting, and then make a square like that. And then the game's still not done. So, so there exists a canonical, I should say canonical actually and functorial. So functorial, so if you have two self-maps of the same degree, of m and n, and you have a map from m to n, it's clear what it would mean for the self-map for the map from m to n to commute with these two self-maps up to homotopy. You just write down the commutative diagram. Two equivalence classes of self-maps, you have a map between m and n, and given two equivalence classes of self-maps on m and n and a map between m to n, you could say that commutes with the self-maps if, again, after raising to some powers, they have the same degree and the diagram you write down commutes. And this is enough to get maps between these constructions.
The functoriality is relative to what? To maps from S mod P to the N to another?
Any map of spectra from anything of this form to another thing of this form, yeah.
To even maps of some degree or just one of degree 0?
Any degree, yeah. And in fact, you can take anything in the thick subcategory generated by this, and you still have these V1 self-maps, and they're functorial in the same sense. So now we do this. By this I mean you take S mod P, and then you have this V1 acting on it, and you mod out by V. Then you mod out by V1. Kind of have to do it in this order. Called V2, such that, and then again you have the same conditions that it's neither nilpotent nor an isomorphism. So you're doing something non-trivial when you use it. And then I'll say etc. So you have P, when you invert P, you're happy. When you mod out by P, there's something else you can invert. You do that, you're happy. Then you mod out by P and V1, and you're still not happy because you have V2. You invert V2, you're happy. But modding out by V2, there's still something else you can mod out called V3, and so on.
Why when you invert V1, you are happy? Because this look like a field? Or?
It looks like a field, yes. I haven't told you anything that justifies that yet, but it's true. Yeah. So the thing that justifies that is that when you so these S mod P to the N V1 inverse, well, maybe not. Maybe let me not try to say exactly yet. We'll see it a bit later. So then, okay, we have a definition. So a P local spectrum is called LNF local if this process stops after n steps. So if x mod P V1 Vn is equal to 0.
Moduli V1, then moduli.
Yeah, and by this I mean you take x and you tensor it with sphere mod P V1 up to Vn. Yeah, that's what I mean by x mod P V1 up to Vn. So the interpretation would be that so x lives over a Zariski open subset of spec S. Namely the complement of the vanishing locus of, so to speak, the vanishing locus of these functions here. But it's a bit different. We don't have globally defined functions or elements because V1 only appears when you mod out by P. And V2 only appears when you mod out by P and V1. And so on, so that you kind of have to do this inductively. Let me draw a picture of spec of the sphere spectrum. So to speak, I mean. So we have open subset, which looks like, Q. And then we have slightly bigger open subset. So this is the L0F local part. And we have a slightly bigger open subset, which is the L1F local part, L2F local part, and so on. And then it kind of keeps going like that.
And you have, outside of this, you have spec of Z mod P somewhere.
Yeah, exactly. But we're not going to go too far outside this. We're going to stay inside. Usually we'll be staying inside some fixed open subset. Yeah. Yeah, and then each stratum, so each stratum is a point. So that's the thing where if you mod out by P and then invert V1, it feels like you're working over a field or a nilpotent thickening of a field. There's nothing else to invert or mod out by that's non-trivial. That would give a non-trivial way of decomposing it.
So is it like with schemes under certain conditions, if you want to classify triangle in some category, or with the right category, you get certainty related to subset of the...
Yes, exactly.
So is it
Yes, yes. Yeah, this is justified by the thick subcategory theorem. I'm not gonna emphasize this perspective, but Devenitz, Hopkins-Smith. So that was the nilpotence 1. I referred to nilpotence 2 earlier. That's nilpotence 1. It's actually a precursor to this whole discussion of VN self-maps. Okay. Yeah, so maybe I was going to do an example. So example, so n equals 0. X is L0 F local if and only if X is rational. N equals 1. X is L1F local if and only if X mod P is V1 periodic. Which just means that this self-map is an isomorphism on X mod P. Remembering that the self-map is of a certain degree, this would mean that the homotopy groups of this spectrum X mod P actually have some periodicity of degree, a multiplicity of 2 times P minus 1. It's also or you can put, it's equivalent to put any n there. So for example, Ku, the topological complex K-theory spectrum, is L1F local. And in fact, you have this bot element in degree 2, which gives a self-map because Ku is a ring. And if you take bot to the P minus 1, it functions as a V1. On Ku mod P. So this V1, another way of thinking about this V1 is it's some kind of version of bot periodicity that you can find in any spectrum.
Okay, so this you're using the ring structure on Ku.
Correct.
Which is, and so Ku is which kind of ring? Is it like
E infinity, it's E infinity, yeah.
What did you write? Ku bracket top?
Topological complex K-theory. Yeah, you see this is, Ofer, I didn't write it in script and all of a sudden it became illegible. Yeah, that was my fault. Okay. So this is like, I said this, yeah, it's kind of like living over as a risky open subset. So you can also, there's an operation of localizing to this subset. So there exists an initial map. So M to ln Fm such that ln Fm is ln F local. And how would you calculate this thing in terms of these PV1 up to Vn? Well, it's not as simple as the situation in usual algebraic geometry because, again, this one only appears when you mod out by this one. So it's not like you can just invert P and then invert V1 and then invert these and then glue them together along the common intersections because you don't have V1 yet. You haven't, globally, you only get it when you mod out by P. So you kind of have to do it a little differently, inductively. So inductively, so the difference between, so ln F is going to definitely map to ln minus 1 F. And then Exactly, you use the completions. So there's something called, I'll explain the notation later, but there's something called LTNFM, which you can actually access as inverse limit over, no, not n, let's say capital N, m mod p to the n, v1 to the n, vn minus 1 to the n, and then you invert vn on the inside of the inverse limit, and then pass to the limit over capital N. And then here, you can do ln minus 1 f lt and m. And this is a pullback here. So you can, when you complete this along the previous guys, you get this thing, which you can directly write down as a functor of m. And then, so this, yeah, then you get a pullback square like this, allowing you to inductively understand this guy in terms of this guy, as long as you can understand this guy, which is where you complete along the previous guys and invert the last guy. So it's like kind of a Zariski open subset of a formal scheme in some sense. All right. Yeah, and this square is very much like the square I had at the beginning with inverting p and completing along p. Okay. Any questions?
So what are the powers that are really defined? You said V1 is really not. So when you want more powers of P, you need to take higher power to define.
Exactly. Correct. Yeah, this is an interesting point. So when you take, if you can choose a V1 self-map on S mod P, it has some degree, maybe 2P minus 1 if P is an odd prime. But then when you go to sphere mod P squared, you have to increase the degree in order to see V1. So a K1 local spectrum is not actually going to be have periodic homotopy. It's only going to have homotopy that's periodic mod P to the n for every n, but with increasing range of periodicity. Yeah. Okay.
So then here, when I'm modding up by increasing powers.
Yeah. You have to fix a V1. You fix a P. Well, okay. You take a P. You fix a V1.
Last week,
Yeah. Yeah, you have to know that you can make all this compatible, but yeah, maybe you should take this as a heuristic. Yeah, but you can choose them all compatibly by this functoriality of Vn self-maps. Don't worry, the legitimate work has been done to make sense of all of this in the literature, and it's all well defined, but I'm just trying to get, yeah. Okay. So that's funny. That's this new picture you get for the sphere spectrum, that it has somehow different, spec S has these infinitely many points associated to any prime number, this chain of points. This might seem a little strange, but let me tell you that there's an algebraic analog, which is very important in the story. So there's a certain structure. So R, a commutative ring. Oh, let's say ZP algebra. Doesn't really matter, but so a certain structure on R gives rise to very similar sequence of elements, also inductively defined, as what we saw in the situation with working over the sphere spectrum. And what is this certain structure? It's a one-dimensional formal group. Now, I'm putting one-dimensional in parentheses because from now on, for me, all formal groups will be one-dimensional. When I say formal group, it's always going to be one-dimensional. Let me remind you of the definition. So a formal group over R is a formal scheme over spec R, yeah, equipped with an abelian group structure let's call the formal scheme G, such that Zariski locally, say, on R, we have that G identifies, forgetting the group structure, with spoof of a power series ring in one variable over R, such that T equals 0 corresponds to the identity section with respect to the group law. So the first approximation, forget about this Zariski locally, so let's just pretend you globally have this coordinate. It's not part of the data, but it exists. But given a coordinate t, the group structure is encoded in a single power series in two variables. So let's say mxy such that, for example, associativity mx myz equals mxy mz, commutativity mxy equals myx, etc. And this is a power series, formal power series over R in two variables, such that it kind of defines it's a group homomorphism, a formal group homomorphism. Okay. And it should start as x plus y. Yeah. All right, so what does a formal group give you? Well, the first thing it gives you is a line bundle. So given G over R, we get omega G. So we take the pullback on the identity section from the Kähler differentials. So this is the cotangent space to the identity for the group structure. This is a rank, locally free of rank 1 R module. But we also get something else. These PV1 up to Vn. So let me make a little lemma. So suppose R is an FP algebra. So given any homomorphism of formal groups over R, say from G to H, the following are equivalent. So the first, so we get an induced map. Let me call this, this homomorphism F. We get an induced map on cotangent spaces at the identity. So and we can ask could this be identically 0? It's a map of R modules. And the second condition is that F factors, and it will be necessarily uniquely through the relative Frobenius. So we have the Frobenius twist of our formal group because we're over an FP algebra. we have our given homomorphism F from G to H, and the condition is that there exists a necessarily unique homomorphism making this diagram commute. Let me just give a sketch of the proof. Well, you vanish a cotangent space at the origin, but you're also a homomorphism, so you can shift that around and you get that you vanish on the cotangent space everywhere. So basically you're a function whose derivative is identically 0. So if you have f of t in R bracket t, such that f prime t is identically 0, this formal power series, then f t is equal to g of t to the p for some unique g in R power series t. So this is an obvious lemma in algebra, or just, yeah, well. Okay. Yeah, and this is just fancy translation of this fact here. No, let's do an example. So example. So let's take the multiplication by p map. Oh, it's from G to G. We have fix any G. We take the multiplication by p map from G to G. The induced map on the derivative of this map is equal to 0 because, well, yeah, the leading term is always going to be p times x. So this we can that satisfies condition 1. So by condition 2, we get a unique factorization through the relative Frobenius. And this we call capital V1. And then we can ask what the effect of V1 is on the cotangent space. And then we get something called little v1. And where does this live? It actually lives in omega g tensor p minus 1. The reason is that the cotangent space of the Frobenius twist is the pth tensor power of the cotangent space of G. So we'll be getting a map from from omega G to omega G to the P, but that's the same thing. It's a line bundle. You can tensor by the inverse. That same thing is giving a section of the P minus first tensor power. Okay? But then if V1 equals 0, then we get a factoring again. So G V1, GP V1 to G. We have the second Frobenius twist. Then we get a factoring like this, V2. And now on cotangent spaces at the origin, we'll get a little V2 in omega G tensor P squared minus 1, and then et cetera. So the conclusion is,
Could you explain again how do you get section?
oh, you look at the induced map on omegas associated to V1.
Oh, sorry, yeah.
Ah, okay, that's all you needed. All right. Yeah. Okay. Yes.
So this capital V is this Verschiebung?
Yes, Verschiebung, exactly.
So the name for little v is because of that.
Yes. Yeah, they're called Hasse invariants, these V1. So these are kind of higher Verschiebungs, somehow. Yeah. Okay. So this gives the construction. These are Hasse invariants. So given G, a formal group over R, a ZP algebra, get a sequence P, V1, V2, dot, 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 or, well, where? And where do they live? So Vn lives in, you take omega g tensor p to the n minus 1, and then you have to mod out by the previous guys, P, V1, V2, up to Vn minus 1. So and the modding out makes sense, because it makes sense to mod out by a section of a line bundle. Because modding out by an element, it doesn't depend on, if you multiply that element by a unit, it doesn't change the answer. Okay? So,
But so it doesn't necessarily go on forever, right? You can only keep doing the process if.
yeah, but I base changed now. I base changed, because I'm modding out by these, I base changed to a ring where V1 equals 0 by construction. So then I do get my V2.
Yeah, and if it is GA, formal, you go on forever.
You go on forever with GA, exactly. Just like with HZP in the chromatic story. Yeah, and it's Eilenberg-MacLean spectrum, ZP in the chromatic story. Okay. Right, so this is very similar to what we had in stable homotopy theory. So it's just like before. With maybe omega g corresponding to, I don't know, the negative 2 sphere, something like this, if you keep track of the degrees. So that's a sigma minus 2 of the sphere spectrum. Okay. Let me make one small remark, and then we'll take a little break before moving on. So remark. But in the stable homotopy theory story, we were not just modding out by P and V1 and so on. We allowed ourselves also to take powers. And you could do that here too. So on R mod P to the N, you have a power of V1. On R mod P to the N, V1 to the M, you have a power of V2, etc. And this is actually purely formal. You don't need to know anything more about formal groups. Okay, I'm using the word formal in 2 different ways. The reason for this is a very simple algebraic fact, which is also important in the chromatic story we were explaining earlier. So the reason, so if R is a Z mod P to the N Z algebra, and I is a nilpotent ideal, and you have x, y in R such that x minus y is an I, then x to the p to the k is equal to y to the p to the k for some k. So if you trivialize your line bundle and you lift your V1 arbitrarily to some higher power of some R mod P to the N, then the difference between the 2 lifts will go away once you raise to a sufficient power. So it'll actually be a well-defined section of the line bundle. And the same story with all these other ones here. So it's really exactly similar to the situation in stable homotopy theory. And let's take a 5-minute break, and then I'll continue explaining this is not just a coincidence, obviously. Okay, so let's move on to the relationship between the 2 pictures. Between stable homotopy theory and formal groups. So we're now, I'm going to change my notation a bit. So now R will be a commutative ring spectrum. you might ask what I mean by that, and for what I'm about to say, it's sufficient to just think of so you're given certainly you're given some multiplication map like this, and it should certainly be commutative, associative, and unital up to homotopy, and that's actually sufficient for what I'm going to talk about. But in practice, I want it to be as structured as possible, like E infinity, and I'll be allowed to guarantee that in the examples I'm talking about. And that just means you have all the necessary higher homotopies for it being truly commutative and to have a well-functioning theory. Okay, so for example, so pi 0 of R will be an ordinary ring in either case. Ordinary commutative ring. So you can think of this also as a way of providing extra structure on an ordinary commutative ring. Sort of like, and now we'll relate it to the extra structure discussed previously, namely putting a formal group on an ordinary commutative ring. Okay, so definition. So R is even periodic if, so the following conditions. So the first condition is even, which is that the homotopy groups are 0 if I is odd. And the second condition is that if you take pi, and this is periodic, of period 2, so to speak. So if you take pi I of R, tensor over pi 0 R of pi 2 of R, that always has a natural map to pi I plus 2 of R, and you require this map to be an isomorphism for all I.
In particular, pi 2 and pi minus 2. So then that modules.
Yeah, so so the remark which Ofer just made is that it follows that pi 2R is a invertible pi 0 R module. That's what you get when you take I equals minus 2. And so we have the odd homotopy groups are 0, but the even homotopy groups are all just tensor powers of this pi 2R. And the tensor is over pi 0R, of course. So this is the periodicity. Now, if this is a free module and you choose a generator, then you see an honest periodicity. Like all of the homotopy groups even homotopy groups will be isomorphic via multiplication by a power of that generator. Sometimes these are called weakly periodic when the module is not free, when this pi 2R is not free, but I'll just say periodic. Okay, so there are examples, thankfully. Well, one is maybe periodic Eilenberg-MacLane spectrum. So just direct sum over all I and Z. Take Z and then you give it an even shift. This can be, it's easy to write down a CDGA structure, giving this because the shift is even. So this comes from a CDGA. But another example is KU, again, this topological complex K theory. So this has the same homotopy as HZ periodic, but it's different. Actually, we can prove it's not isomorphic if you believe everything I've told you up to this point, because when you take KU mod P, I told you that's V1 periodic. But But if you take Hz periodic mod P, it cannot be V1 periodic, because it will be a direct sum of things which are concentrated in a single degree, and if you have something concentrated in a single degree and you invert V1, just for degree reasons, you'll get 0. So, yeah. So this Ku as a spectrum does not split as a direct sum.
So on spectrum, especially many homotopy groups, because of the degree of this VI, all of them are nilpotent.
Or even if the homotopy just, there's no homotopy in high enough degrees, then when you invert V1, you get 0.
Okay,
Yeah. Yeah. Yeah.
Yeah.
Yeah. Yeah, this leads to some strange phenomena, which we'll discuss later, strange and important phenomena. Okay, now there's a construction due to Quillin. Which started the whole theory. So if for R even periodic, then you get a formal group over pi 0 of R. Canonical formal group over pi 0 of R. Namely, so it's called the Quillin formal group, so GQR, it's spoof of, so you take, now I have to, infinite complex projective space, so I'll have to explain this in a second, but up pi 0. Okay. So remember when I didn't define what a spectrum was? That's obviously that's bound to cause some issues at some point, right? But well, one thing that traditionally spectra arose as cohomology theories. So every spectrum gives you a cohomology theory on CW complexes. But so maybe in modern terms, I mean, you have so you have anima, which is just CW complexes with weak equivalences inverted. And as a point, this is free, not necessarily stable, so co-complete on one generator. And then we had spectra and the sphere spectrum, which was free stable. So in particular, there's a natural functor here, which traditionally is called suspension spectrum, but let me just denote it. So if you have an anima, then what it really is like the free, it's an analog of taking the free abelian group on a set. So I'll use the same notation for it, sphere bracket K. So this is like, in traditional notation, it's sigma infinity plus K. And then, so this R to the K is going to be the internal hom from this sphere bracket K to R. So pi 0 of R to the K is the degree 0 cohomology of K according to the theory. But this is also a ring. This is also a commutative ring spectrum. Because it's basically, you have a ring and you're taking functions from a set to that ring, and there's pointwise multiplication. Formally, it's because this is like a coalgebra and this is an algebra. This is a coalgebra via diagonal map you have on any space, and so on. Okay. So then, and CP infinity is the, but this cohomology theory, note that this sends colimits, so this K goes to R to the K is really a cohomology theory, so it sends colimits to limits so that when you look at something like this, it's going to be an inverse limit of, when you write this as a union of finite things, which is the CPNs, then this is going to be a limit, so this ring of functions is going to have some formal nature. It's going to look like something complete. So it's better to consider it as a spoof instead of a spec. So then the way you do that is spoof of this is the same thing as the colimit of the specs of these things, which are kind of finite because this is a finite CW complex. Okay. Sorry?
So the sentence of explaining pi 0 of
Yeah. It's the degree 0 cohomology of K according to the cohomology theory R. So for example, let's do an example. So if R were HZ, then pi 0 of, so the Eilenberg-MacLane spectrum will just be the usual cohomology of K with, zeroth cohomology of K with coefficients in Z. So if R is this periodic version, then this pi 0 R to the K is the product over all I in Z of H2I K Z. So it's the, and if R is Ku, and let's say K is a finite CW complex, then this is the K0 group of complex vector bundles over K.
So we can also think like the space of functions from CPN to it depends only on R on the connected part of the spectrum.
That is correct. That is correct.
Okay, so you can think of it as a kind of a function space, and then you can try to say, well, you can try to calculate it using Korsnikov invariants, Remarkably, you try to lift.
Yeah.
Cohomology classes on CPN, these values, and since R is even, you are in somewhat better shape, but so you get successive, so you don't get a precise description, you only know that successive invariants.
Right.
And so it is some twisted form of this formal series thing, but it's not exactly. I mean, you know that there is this twist by pi 2, but still, it's not. You get it only up to this.
No, but the evenness helps you. So here's the. So why is this a formal group? So why is it locally isomorphic to spoof R power series T? So well, locally. So locally, you can choose a generator. Let's call it alpha. A generator, a free generator. Now let's look at, for example, R CP1, the very first step. So the cohomology of first complex projective space. We can restrict to infinity, and we get, well, a map to R. And the kernel or the fiber term is like the cohomology of, by definition, say CP1 relative to infinity. But this is pointed S2, so we're looking at Homs from pointed S2 to R, so that's just a shift of R. So that is sigma minus 2 of R. So whatever this thing is, it sits in a cofiber sequence with R and sigma minus 2 of R. The claim is that this cofiber sequence splits. So this splits by evenness.
Not only on homotopy groups, but it actually splits.
It actually splits as R modules, as R modules.
Okay, because you split it by 0 and the generator, and then you.
Yeah, let me try to explain. So this is viewing this as a cofiber sequence in R modules. There's the thing that classifies it is a boundary map which goes from R to suspension of R. But because we're working in R modules, homomorphisms from R to suspension of R, this is just in bijection with an element in pi1 of R, which is equal to 0 by evenness. So there's no room for non-trivial extensions when you have an even theory and you calculate the cohomology of CP1, there's no room for non-trivial extensions. And so you can choose a splitting, which gives you a kind of a class T in here, T in pi0 here, which projects, well, why am I saying this? Well, you can choose a splitting for CP1, and then for CP2 you get a similar story. You're just adding another even cell, and then there'll be an S4 instead of an S2, but again by evenness everything has to split. And in the limit you see that this thing, well, inductively you see that this can be identified with pi0r bracket t mod t to the n plus 1. Did I get that right? Yeah. And then in the limit, you see that you are getting a formal power series ring.
Speaking should be sigma minus 1?
Sigma minus 1? Yes, thank you. Yeah, thank you. So one of the main things in chromatic homotopy theory is that apparently this very simple guy contains a lot of secrets, or the cell structure in this very simple guy contains a lot of secrets. So it just even cells. You have a 0 cell, you have a 2 cell, you have a 4 cell, but the attaching maps are actually much more rich than you might think. Like maybe you think you understand what complex projective space is, but no, you don't, because the attaching maps contain many secrets. And even periodic theories are ones which kind of get rid of that, so that you can see phenomena more clearly.
Yeah, so if you're doing the CPN, you will get, again, RCPN going to RCPN minus 1, and then some sphere. This is as R modules, but then you want to look at the ring structure coming from the ring structure on R.
Yeah.
And of course, those are also ideals in the ring. But then you have to show that the pi0 multiplication somehow you get the classes you have defined using the suspensions of R should multiply correctly.
Yes, that's right. So we choose a class here, T, which goes to 0 under restriction to infinity. And then you want to claim that T squared is equal to 0.
But also when you go with the CP2, you want that T squared is the one that you get in CP2, comparing CP2 to CP2.
Yeah, that's true as well. Yeah. No, okay, I mean, I was explaining it in a bit of a down-to-earth way, but I mean, you can also, yes, I mean, you need to check all of these things. So, so how would you, can I explain this in a down-to-earth way? Okay, the way people usually explain this is using the Attili-Herzebusch spectral sequence, which goes from cohomology of, say, CPN with coefficients in the homotopy of R to the R cohomology of CPN. And then, since both R and CPN are even, there are no differentials in this spectral sequence. And then if you just choose a T, which is detected by, you can choose a T which is detected on the, which kind of looks like it does what you want on the E2 page, and you can lift it to something in the homotopy of R. Then the powers of T will have to form a basis. And you can also check that T to the n plus 1 is equal to 0. There's different possible arguments for that. I mean, one is just that, well, never mind. one can do all of this. Let's say I'm giving an idea here. All right, so that's why it's locally isomorphic to spoof of R power series T, but why is it a formal group? Where is the group structure? So, well, it comes from the fact that this CP infinity has another interpretation up to homotopy. It's KZ2. So, Eilenberg-MacLane spectrum shifted up. So in this notation, or well, it's really Eilenberg-MacLane space in this case. So it's the space that classifies degree 2 integral cohomology. And this has an abelian group structure. So then when you take functions into it, you get like dual to an abelian group structure, but then you take spoof and you get an abelian group structure again. To make this rigorous, you need to know some kind of Kunith result for that the R cohomology of like CP infinity cross CP infinity is the same as the R cohomology of CP infinity tensor, completed tensor, the R cohomology of CP infinity, but that follows again from similar arguments using the evenness that you have these kind of Kunith results which make this rigorous. I won't go into the details about that. So there's an interpretation of this so a choice of coordinate t, and that coordinate will live in this R cohomology of CP infinity. This gives a theory of first Chern classes for complex line bundles. In R cohomology. There's yet another interpretation of this same space, which is the classifying space of the group C cross, or BS1 if you prefer. And in that regard, you can see that the same space also classifies complex line bundles. And so this choice of T, if you have a complex line bundle on a space, by pullback of T, you get something that deserves to be called the first Chern class. And it's the fact that T is a coordinate is reflected in the idea that the first Chern class of a trivial line bundle is always supposed to be 0. And then the formal group law corresponds to giving the formula for the first Chern class of a tensor product of two line bundles. So a formal group, given a coordinate, a formal group is just a power series in two variables. And in terms of this interpretation, in terms of first Chern classes, you get it's explaining the behavior with respect to tensor product of line bundles. So let's do some examples again. So if R is HZ periodic, so then we can choose T to be the canonical class so it lives in degree 0 in the periodic theory, but in the non-periodic theory it would live in H2. Then this gives rise to the usual theory of Chern classes, usual theory of first Chern class. And for that, you have C1 of a tensor product is just the sum of the C1s of each of the factors. So this gives rise to the additive group. Yeah, that's what I'm going to explain next. Yeah. So another example would be R equals KU. Then for your theory of first Chern classes, well, I could just describe it in the universal case, or I could just describe it in general. It's just as simple. Well, there's something obvious you can do. I mean, KU is complex K theory. If you have a complex line bundle, you obviously get a class in complex K theory. But we can't take that because this needs to be satisfied. But we can just do the most naive thing. So we just subtract off class of the unit, say. Then this gives corresponds to a choice of coordinate. And then if you do C1 of L tensor L prime, well, yeah, it's the same as, well, whatever it turns out to be, right? So it's L tensor L prime minus O, which is the same thing as taking L minus O, and then L prime minus O, minus L minus O minus L prime minus O. And then I think that's, did I get that right? Yeah, or something.
Of course, you use periodicity.
Plus.
You use implicitly, you use both periodicity to go to the right degree.
No, I am in the right degree.
No, because you want the Chern class to be in H2.
No, I want it to be in H0. That's my convention.
Okay, but you are working in a periodic rings anyway.
Yeah.
But
This is more canonical. Right, so anyway, so this corresponds to the multiplicative formal group. So if you just take the usual coordinate on A1 and restrict it to GM, that doesn't count as a coordinate for that group, so you need to subtract 1, and then it's clearly exactly the same phenomenon as this. The idea is that the ring structure on complex K theory comes from tensor product of vector bundles. Okay. Any questions about this? All right. By the way, I should say, so the multiplicative formal group, so mod P, V1 is in the Hasse invariant, is invertible. So this is supposed to correspond to the fact I told you that on KU, that KU mod P is V1 periodic in the sense of stable homotopy theory. It's supposed to, matching up with the fact that when you look at the multiplicative formal group in characteristic P, that the Hasse invariant is invertible. Okay, but what about higher heights? Did I define what height is? Maybe not. So when Vn is invertible, then you say that your height n. So Vn first has to be defined. So the previous Vi's have to be 0, or at least nilpotent. But then if Vn is invertible, you say your height n. So here we have a height 0 example, when you rationalize at least. And here we have a height 1 example, but what about higher height examples of even periodic ring spectra? So good ones are the Morava E-theories. So here's a definition. So if R is ZP algebra, G a formal group over R. So say G is of Lubin-Tate type. if, so the following conditions are satisfied. So first of all, I want this P, V1, etc. up to Vn minus 1 to form a regular sequence. These Hasse invariants. That's nice for the purposes of modding out. It means like naive modding out and derived modding out are the same. And the second thing is I want it to be height n, so Vn should be invertible, a unit in R mod P V1 Vn minus 1, so this is saying it's height n. At least once you can talk about Vn. A Lubin-Tate type, let's say of height n, yeah. Right. The third condition will be that R is P V1 up to Vn minus 1 complete. Excuse me? Sorry?
Yeah, it also shows the different interpretations of regular sequence and equivalent.
Okay, that's good to know.
Because you use like the old regular sequence, the first is non-zero divisor.
Exactly.
Yeah, but then you have the Koszul complex and other.
Yeah.
Okay, but then it's equivalent.
It's equivalent. I don't know. I just mean the thing where mod P V1x injectively, mod P and V1 V2x injectively.
Symmetric definition.
Yes, yeah. The whole theory is non-symmetric, so I couldn't. The question of whether it's symmetric or not doesn't make sense because V1 only appears when you mod out by P. Yeah.
Of course,
Yeah. Okay.
I'm a big piece where the VI's live now. Previously the VI were sections on your twisted line bundle from a group.
Yeah.
Yeah, but then it still makes sense because it's a local. You can work locally, lift them, and then get this.
So, yeah. So, for example, what do I mean by it being a unit? Is that the question? I mean that this section is a generator. This section gives an isomorphism from the trivial line bundle to that line bundle. Yeah.
But then also for the regular sequence condition, and I only have Vn minus 1 after I've modeled out by Vn minus 2. So Vn minus 2.
Yeah.
So when I say regular sequence, it's not, I can't rearrange the VI's, in fact, as Arthur was saying.
That's true. You cannot rearrange them. So you can only take the sequential definition, really. Yeah. Okay. So for the last condition is that R mod P V1 up to Vn minus 1 is a perfect FP algebra. So the Frobenius is an isomorphism. Okay, and then I'll say definition. So E, a commutative ring spectrum, is a Morava E-theory of height n if, so first of all, E should be even periodic. And then the second condition is that the Quillin formal group, so over pi 0 of E, should be of Lubin-Tate type, is of Lubin-Tate type. That was this definition here, being of Lubin-Tate type. So then there's a big theorem. Maybe there's this. The first version was done by Morava. Then there was like improved it a bit, and then Hopkins improved it even more, and then Lurie improved it even more, and now maybe this is enough. So if you look at there's an infinity category of Morava E-theories. It's a full subcategory of commutative ring spectra. It's equivalent to an ordinary category, namely the category of pairs consisting of a perfect FP algebra R and a formal group of height n over R. And what you do is you take E and you send it to pi 0 of E mod P V1 Vn minus 1, equipped with the base change of the Quillin formal group of the So this purely algebraic data, if you have a perfect FP algebra and a formal group of height n, you can lift it to the world of spectra in a canonical way. The world of E-infinity ring spectra, commutative ring spectra. And you get a nice panoply of theories which lets you make this bridge between stable homotopy theory and the theory of formal groups. So let's do examples. Or maybe just one example. Yes?
Yeah, here on the right-hand side, the formal group should be a Lubin-Tate, right?
No. No. That's the residue field. So the Lubin-Tate type, you always have these previous parameters. It's so that, yeah, so let me say, so pi 0 E, so I'll make a remark. Pi 0 of E, GQ E. This is also a formal group over a commutative ring. This is the universal deformation of this guy over here. So Lubin-Tate proved that you take one of these guys, maybe they were considering the case of fields, not arbitrary perfect FP algebras, but there's a universal deformation of such formal groups, which adds in exactly this many kind of power series generators, where the last one is sort of Witt vectors instead.
Lubin and Tate already, well, in their papers very old on local class field theory, so this was actually over the ring of integers in a local field. You construct some formal group to do with pi x plus x is a q. So this is just a it's a special case. No,
this is different Lubin-Tate work. I mean, this is not about...
this is not this Lubin-Tate, it's another Lubin-Tate.
Yeah, where they did exactly this. They just studied, you take a formal group over a perfect field, you just study deformations.
Okay, so it's not this paper.
It's no complex multiplication or anything. It's,
okay. It's another, this I didn't understand sometimes.
Okay, so one example at least. So you can take FP and the multiplicative formal group. So, and you can ask what is the, so I wanted to introduce notation. So, well, let me just say it in words. So if you have a pair as on the right-hand side there, then the corresponding E-theory I'll just denote by E of that pair. That's the Morava E-theory. This is just, well, it's basically KU except P completed. And in fact, we sort of already proved this when we calculated that KU has the multiplicative formal group. And it's very simple to see that the other axioms are satisfied. Okay. The higher height examples sort of...
Where does this P completion come from?
Well, in the definition, I mean, well, I asked that pi 0 be p complete, so I have to do it.
Right.
But I mean, there's no way you can go from this to something integral, right? I mean, you start with something over fp. How are you going to jump to? You can maybe do deformation theory and jump to something p-adic, but you can't jump to something integral. So that's yeah. Okay. Let me recall. Yeah. So the higher height examples of Morava E-theories, they don't sort of show up in nature, just like complex K theory does, as far as we know. So you kind of have to build them using formal groups and so on. You kind of have to build them using this theorem in one form or another. So I can't really give you more examples because they're not previously known theories. They are what they are. But okay, let me remind you a bit about classification of formal groups of a given height over an FP algebra. So recall, I think it's essentially due to Dieudonné. So let's say, so any two formal groups of height n. So that, let's say that this means, for an arbitrary formal group, let's say that this means P and V1 and Vn minus 1 are equal to 0, and Vn is a unit. Are pro-étale locally isomorphic. So over FP already, there exists a, say, canonical, a specific formal group of height n. Let's say a unique formal group of height n, let's call it Hn, such that if you look at the P series, it has a coordinate, and the P series is just as simple as possible for a formal group of height n, so t to the p to the n. Maybe this is Honda. It's called the Honda formal group. So, well, okay, if you just look at those two claims, then you understand that classifying formal groups over FP algebras is just classifying forms of this particular formal group here. So then you should study forms, you should study automorphisms. So automorphisms of Hn, this group scheme is pro-constant. So once you base change from FP to the n, then you get all the automorphisms, so to speak. So this is pro-constant with value. So this is units in the ring of integers. In division algebra, a specific division algebra over QP of invariant 1 over n. And was there something else? This should be enough to determine it. Oh yeah, well there's an action of the Galois group here, Fp to the n over Fp. There's also an action here, and they match up. I won't get into too many details here, but well, I mean it's affine and it's spec of. So this is a profinite group. So it's an inverse limit of finite groups. So for a finite group, I assume we all mean the same thing by a constant group scheme on a finite group. We just take the inverse limit in affine schemes.
So the automorphism over a formal group can be thought of as the limit of automorphism group of.
Yeah, of truncations. Yeah.
Commuting up to truncation.
Yeah.
So as a pro thing or as a conjecture.
Yes. It matches up. So it matches up with there's a uniformizer here, or you could even just look at P. In the p-adic topology matches up with the, it's.
And how is the Galois group acting on OD1 over?
Well, there's a way of, this is something like, you take like Witt vectors of Fp to the n, you adjoin pi maybe in some non-commutative sense, like maybe pi to the n is equal to p, and then there's some commutation rule, like alpha pi is equal to Frobenius of pi Frobenius of alpha.
Let it act, lifting the action on the residue.
Yeah, well, it's just functorial. I mean, it's just a functorial in Fp to the n. I mean,
Okay, when you write it like this.
Yeah, when you write it like this, it's functorial in the choice of fp to the n. Yeah. Okay. Right.
And for the normalization of Frobenius, which enters the local class field theory, is important.
Yeah, it's a.
In the old days, they used the Frobenius, the piece power Frobenius, and then they used the inverse, and so this one is invariant.
I don't. I'm the only thing I'm not sure about is whether this should be over here instead. I mean, and that does make a difference. I can't remember which one it is, but you know, it's, yeah. Okay, well, the conclusion from all of this is that like the moduli stack of formal groups of height n, so this is just a quotient. So you take spec of fp to the n, and you mod up by a certain profinite group called the Morava stabilizer group. And that is, by definition, Gn is the semi-direct product of the Gauss group acting on this division algebra. Or the units in the ring of integers of this division algebra. So basically, there's only one formal group of height n, but you have to be a little careful. So that's that. And some details of this will be important later, so I wanted to talk about it at least once. Okay, now, so given this, so in fact now the main theme of the lecture, of maybe even the main theme of chromatic homotopy theory, or at least at a fixed height, there exist at least two candidates for a complete local ring of spec S at the height n prime. Spec S localized at P. There exist, let's say, greater than or equal to 2. So there's one. So the first candidate would be this Tn local sphere. So this is from the perspective of these self-maps. So it was this inverse limit of sphere mod p to the n, v1 to the n, vn minus 1 to the n, and then you invert vn, so that you're actually at the height n prime. And the second thing would be this Morava E-theory. And to fix one, let's take fp to the n and this Honda formal group. So this one is kind of, from the perspective of these Vn self-maps, this is clearly the right answer for the complete local ring at the height n prime. You really are just completing out all the previous guys and inverting the next one. But this one is more understandable. So this is more, you know, this one is understandable. At least as understandable homotopy groups. So the homotopy groups are just, you have some bit vectors on fp to the n, and then you have power series and say, some variables. And then you have an invertible class in degree 2, which is some version of Vn. And this is very mysterious homotopy, at least, because it's the way you'd understand it. A priori, you'd first have to understand the homotopy groups of spheres, and then taking mod p, v1, and so on. So the main question is how far apart?
Sorry, a question?
Yeah, just a sec. Yes.
What do you mean by local ring here? So should I take the invariant under this H groups?
No, we'll get to that. So at the moment, I mean, this at least on homotopy groups, it looks exactly like a complete local ring. Yeah, yeah. So that in that sense, it behaves like a complete local ring. Yeah. So the main question is, how far apart are these? Yes.
Sigma 2D what? In the formal series with sigma.
Oh yeah. No. So pi 0 is just this, but then the whole thing is even periodic.
Okay.
So if I want to describe the whole homotopy, I add an invertible generator in degree 2. Yeah.
So it's plus minus 1.
Yeah, plus minus 1, exactly. Yeah. Yeah. And I think well, maybe I'll just say, so let me at least state the telescope conjecture. The telescope conjecture sort of says that the map is faithful. So if X is a Tn local spectrum such that X tensor En, and maybe you want to recomplete at PV1 Vn minus 1. If that is equal to 0, then X is equal to 0. So if you take a module over this guy in this complete sense, and then base change it here, it becomes 0, then it was already 0. And this and there's a theorem. So maybe first, Serre. It's true for n equals 0. Height 0, it's true. Then we have Hesselholt and Miller. True for n equals 1 and all p. And then we have, let me there's 4 authors, and I know them very well, and I respect, but I still, it's nice to, so Burklund-Hahn-Levy-Schlank. It's false for n equals, n bigger than 1, all p. So in the rest of the course, I'll be trying to explain this result and kind of implications, maybe a little bit implications, and but also the way that this goes is by considering algebraic K-theory. So the way that the counterexample for n bigger than 1 comes from algebraic K-theory. So the other main theme of the course is the interaction between algebraic K-theory and the chromatic story. But we'll start on that next time. Thanks for your attention.
So this Tn localization is quite complicated. It's not a smashing localization.
It's not. It's even if it were a smashing. I mean, this LNF is a smashing localization. It's still complicated. I mean, it's more complicated even than Tn localization. Yeah.
But so this Tn local spectra, it's not enough to consider just the case of spheres in particular. So this.
No, in fact.
And the counterexample is.
No, if you take something coming from a finite CW complex, then this is true, and it's essentially the definition. So I didn't explain to you what a Vn self-map is, but you use this theory, En, or En mod PV1 up to Vn minus 1, which is called Morava K-theory. You use that theory to detect what a Vn self-map is. So this question is really only going to be interesting for really infinitary X. So if you start with something like related to the sphere too much, you're never going to find a counterexample.
Do we have a nice description of T and local maps between two spectra?
What exactly do you mean by that?
Maps that become equivalents after Tn. It is LTN.
Maps that become equivalent. Well, it depends what you mean. So, I mean, you could take the cofiber of the map, and then the same. It's equivalent to ask a criterion for when an object has vanishing Tn localization, and then, so if you take x mod pv1 up to vn minus 1, and then invert vn on that, you get 0. Other questions?
So is this localized the spectra? Is it idempotent algebra?
This one? Yes. No. LNF is. So. But this one has some completion in it, so it's not idempotent.
Because you kind of has to invert Vn and then you do completion. It's
yeah.
Not commutable.
Yeah. Okay, well, let's call it quits then for today.